Okay, hey everyone. So today we're going to be doing something a little different. Our topic for the day is backpropagation, which is an algorithm we use to train our neural networks. And we've been talking about neural language models, so we're going to look more specifically in that context today. But instead of me talking over a bunch of slides, I've got this iPad. Whoa, it's weird. And I'm going to be writing on it instead of the standard lecturing. So this is my first time doing this. I hope it is somewhat watchable. Let me know on Piazza if I should continue using this format going forward or stick to slides or maybe do some combination of both. Okay, so let's kind of start with an overview of what we're going to talk about today. So first, brief review of neural language models, focusing on things like what are the parameters, and this is going to kind of frame the discussion of gradient descent and backprop later. Next, we're going to talk about gradient descent, which is an algorithm that we use to train our neural networks and, of course, many other machine learning models. For those of you who have taken a machine learning class before, you are certainly familiar with this concept of gradient descent. For others, we'll briefly review the algorithm here, and you should also plan to read more about it on your own if after you watch this video you're still confused. The next thing we're going to talk about is backpropagation, which is really a way to compute the gradients. And we're going to go over this in both a single neuron setting, which makes it easy to explain the intuition, as well as a backprop of a linear layer, which we've seen before in our neural language models, right? The linear layer is used to project the concatenated word embedding sequence into a hidden space. So these two concepts are used to train NNs, neural networks. And in our context, we're going to use it to adjust the parameters of our neural language model such that it makes better predictions of what the next word is. All right, so that's a quick overview. Now let's briefly review that feed-forward fixed window language model and just use it to identify things like the model parameters, which we're eventually going to be computing gradients on. So if you remember, we had this prefix from last time, and we started with these word embeddings for each word in the prefix. In our feed-forward fixed window language model, we concatenated them all together, and we passed that through a hidden layer. Then we used the resulting representation to predict the word books, and we did this using the softmax layer. So we went through the forward propagation phase of this model last time, but now I wanted to kind of emphasize what components of this model are the actual parameters. So remember, we have the word embeddings, C sub 1, C sub 2, C sub 3. These are associated with each of the words in the prefix. And remember, they're low-dimensional, real-valued vectors. So when we start training this model, these embeddings are randomly initialized, say. They don't have any correspondence with the semantics or syntactic role of the word that they're associated with. But we would hope that once we train the model, adjust the values in these vectors, that the vector space of the word embedding starts becoming more meaningful. So remember when we did our hidden layer projection, we used this parameter matrix W sub 1. Similarly, when we did our softmax layer, we used this other parameter matrix W sub 2. So when we wrote down the equations of this model, it looked kind of like this. We had H equals F of W sub 1 times C1, C2, C3. So this is the concatenated representation. Then let's say we had O, which is our output probability, which is the softmax of W sub 2 times H. Right? So here, note that we have two intermediate variables. We've got, okay, let me use a different color. We have H and O. So H and O are not model parameters. I use the same color. This color thing is pretty cool. So H and O, is that readable? Yeah, maybe. Are intermediate variables, not parameters. If you look at these equations, they are functions of the model parameters, which are, I'm probably going to go overboard on the highlighting. Apologies in advance. Oh, wow, that's not even the right color. But the highlighted things are the model parameters. So the highlighted things are what we're going to adjust. And what we eventually care about is that the output of this softmax layer, right, this probability distribution O, is more in line with what we would expect to predict. So for this prefix, maybe assigning a high probability to books. Okay, and so here we've got our model parameters. Our model params. Now, how do we train them to yield good predictions? Apologies for my handwriting. You're just going to have to deal with that for this lecture and also other lectures in which I use this iPad. So this is a question. The answer is gradient descent. So we are going to look at gradient descent as kind of broken down into three different steps. So the first step is we need some way of determining how good our current set of parameters is at predicting the next word, right? So we need to measure that somehow. And we're going to do that by defining a loss function. We'll call it L. And L is a function of our model parameters. We commonly use theta to refer to all of our model parameters. So if I look at the example from above, we highlighted all of these model parameters for our neural language model. So for NLM, we had W1, W2, C1, to how many ever words are in our vocabulary, right? So the C's are the word embedding. So the theta in this example would correspond to all of these parameters. This is supposed to be an arrow. But I'm writing this now more generally. This theta could be the parameters of any model. And this loss function L theta is going to measure how bad the current model is at, in our neural language model example, predicting the next word. But this objective could be different for different tasks, right? It could be, answering a question or predicting the sentiment or so on. You just need some scalar value that defines the current performance of the model. Okay, so once you have a way to measure how well your model is doing, the next step is to calculate the gradient of this loss function with respect to the model parameters. So we're going to use this notation, dl d theta, to denote the gradient, and we're going to use it for all of the partial derivatives that this gradient encompasses in the future. Okay, so what exactly is the gradient? For those of you who are unfamiliar with it, it basically tells us, so I have the scalar loss function, and let's say I have a particular parameter in my model. If I change that parameter, if I increase that parameter, how much will the loss function increase? And in general, this gradient is giving us the direction of steepest ascent with respect to all of the model parameters. So let me write that down. The gradient, I mean, intuitively, it tells us how the loss changes when we modify the model params theta. And importantly, it gives us direction of steepest ascent. This is important, so we will highlight it. Okay, so I'll give you an intuitive example of this in a bit with a very, simple function. But before I do that, so we've defined our loss function, we've computed this gradient. How do we use the gradient? What we're going to do is take a step in the direction of the negative gradient. So remember that if the gradient is giving us the direction of steepest ascent, so increasing the loss, we know that the loss is telling us how bad the model is currently doing, right? So we want to actually minimize this loss function. So going in the direction of the negative gradient will take us in the in a direction that minimizes this loss function. So minimizing the loss. So what does it mean to take a step in the direction of the negative gradient? So let's say that our model parameters were theta old. These are our current model parameters. And we want to get a new set of parameters, theta new, that that result in a lower loss. So to do this, we're going to take our old parameters and we are going to subtract this eta multiplied by the gradient. And so what is eta here? Eta is a variable that corresponds to something called a learning rate, which controls the step size. So how much of a step we want to make in the direction of the negative gradient. Seems highlighter worthy as well. Okay, so that was a lot of information. Let's look at a simple example that'll hopefully make it more clear. So let's just look in a two-dimensional plot. I have one parameter and one loss function. Sorry, I have obviously a scalar loss function. So we have our loss on the y-axis, L sub theta, and we have theta here. So let's say theta is also a scalar here. And let's say the loss function looks something like this. So this is a convex function. In practice, we won't be dealing with functions like this, but we're still going to use gradient descent. This is just for demonstration. All right, let me pick a different color. So let's assume that I randomly initialize theta. So I have no idea before starting training what the best value of theta is that minimizes this loss function. So maybe I start up here. We'll say this is random initialization. So I set my theta to some value over here. I compute the loss function over my training data, and I find that it's pretty high. So now I'm going to compute the gradient, right? And so I compute the gradient at this point. It's this line here, this tangent line, and I decide to go in this direction, right? The direction of steepest descent. So maybe I take a step in this direction, and I end up over here with my next, when I use this update function. So this one was theta 0, our random initialization. This one is theta 1 after one step. And this direction here was given to us by dl d theta 0. Okay, so now we're going to just repeat this process. So I'm going to compute a new gradient, go over here, compute a new gradient, go over here, and eventually maybe I finally reach the bottom here, the minimum of this function, and I claim that I'm done. I've reached the minimum loss. So my goal is to get to this point. And the way in which I'm going to do that is by computing these gradients, taking a step in the direction of the negative gradient, where this learning rate value controls how far I step. So as an example of what happens if I have a big learning rate, imagine that if I had a huge learning rate and I started back at this point, the randomly initialized point, I do run into the danger of completely overshooting the minimum and ending up on the other side here. And that's obviously not good. And if my learning rate is too large, I might see an kind of zigzag pattern of my loss function where eventually I might get to the minimum, or I could just overshoot it completely and go somewhere else in the parameter space, which results in a higher loss. Maybe I'll get rid of these. That was just a demonstration of what happens if your learning rate is too high. So in general, a learning rate is part of your model hyperparameters. So a hyperparameter refers to something that is not learned by the model, but is rather something that you as the designer of the model set before the training process even starts. In general, you might have to train multiple different models using different hyperparameters before you can find one that maybe results in the smallest loss. So hyperparameters are tuned. I mean, in most cases nowadays, they're, I think, still chosen roughly manually. People who have a lot of experience training neural networks tend to know what range of hyperparameters tend to work best for given problems. There's also a whole research field on optimizing these hyperparameters automatically, but we're not going to talk about that in this class. Okay. So, right, going back to this, you might wonder, well, for such a simple function, can't I just get to the minimum, compute the minimum in a closed form and not have to go through this, this whole process of iteratively computing the gradient and adjusting my model parameters? This is true for simple models, like least squares is a famous example that have closed form solutions, but in practice, when you're dealing with these neural networks that have, highly nonlinear relationships between inputs and outputs, we went over that last time, there is no closed form solution for computing the best set of parameters. All of the loss functions we deal with are non-convex, and we still use gradient descent to approximate the minimum. So none of the methods we're using guarantee that we're going to reach the global minimum of the the set of parameters that reaches the global minimum. But in practice, these methods, gradient descent seems to give you a reasonable solution in most cases. I should also mention that this update rule here is just vanilla gradient descent. In practice, there are several more advanced optimizers, things like Atom or AdaGrad that people might have seen if you've dealt with neural networks before, they're all kind of just variants on this equation with clever methods of determining step sizes adaptively and so on. Okay, so that is the high level of gradient descent. So hopefully at this point you understand why we are computing these partial derivatives. It's because they tell us the direction of steepest ascent, and then why we're stepping in the negative direction of that so that we can minimize our loss function. So hopefully that's all clear. If not, I'd encourage you to do more reading on just general machine learning materials, and maybe I'll put some links to those on Piazza or the website. Okay, so now that we've gone over at least this high-level process of gradient descent, let's look at a concrete example. This one is going to be fairly straightforward, but this is also going to serve to introduce backpropagation, which is a method that we use to more efficiently compute the gradient. So we'll look at this in a single neuron example. So we'll be dealing with completely with scalars, no matrices or vectors in this example, just to make things easy. So let's depart a little bit from our neural language model framework, and because that's kind of hard to do in this toy setting. Instead, let's just say we have a generic problem where we have some input. Our input is a single number. We multiply that number by some scalar weight, again, just a single number, to get some hidden representation. Then we multiply that with another weight, w sub 2, to get a scalar output. All right, so one question that you should be able to answer at this point is what are the model parameters? Okay, so in this case, we have just two model parameters. We have w sub 1 and w sub 2. X is our input, so X in this case is not a word embedding that's learned by the model. X is just a number that we observe in our training data set. And so maybe I'll make that more clear. Our parameters are w1, w2. Inputs look like X, Y pairs. So X is a single number input, and Y is the target output in our training data set. So we're just trying to learn a function to map one number to another number. And our loss function is going to be defined by how close is the output O to the target output Y. But before we get into that, let's look at how we compute these intermediate variables. So let's define this first equation as tan h of w1x. So here we're introducing a new nonlinear function. Tan h is a common activation function used in recurrent neural networks, something that you should be familiar with. Okay, and let's say O also uses a tan h of this product. So again, here note that we have two intermediate variables, right? We have h and o. These are not our model parameters. They're intermediate variables. We don't have to compute derivatives with respect to h and o specifically to do our model updates, right? Our model updates, our theta is just w1 and w2. Okay, so let's state this again a little more concretely just to make the training situation more clear. So let's say assume our wow, that was terrible. Our inputs are x, y scalar pairs, and our goal, we want to predict y from x. So what do we do here? The first step is something that we've seen before. It's called forward propagation. So given an input x, different highlighter. So given, maybe I'll do this too. So given an X in our training data set, we will first compute the value of each neuron. So here I'm using the term neuron to refer to these three like nodes in this graph. So the input, the intermediate, and the intermediate variables here. O is actually our output. Compute the value of each, what is I trying to say? Each neuron. So these are H and O. Using the model equations. Okay, so let us make that more clear. What are the model equations? They're these two things. Okay, and next, what are we going to do? We're going to predict the value of y. Actually, this is not really a separate step. We did it in the first, but the first thing, but our O value is going to be the model's prediction of y. And finally, what do we want? What is our goal? Goal, make O as close to y as possible. Wow, okay. So this is all stuff that we saw from before. Let's look at step 2. Step 2, compute the loss function. So this is going to tell us, I don't even know why I'm doing these highlights. So this is going to tell us, it's going to measure that closeness, right? So since we're in this simplified case, we'll just use the square loss. In this example, for simplicity, in the next video, we're going to look at the loss function used for neural language models, which is a cross-entropy loss. But here we'll stick to something simple. The square loss is just defined as follows: our ground truth minus our prediction squared. So obviously, if O and Y are close to each other, then this loss function is going to be low. If O is a terrible prediction of Y, then this loss will be high. So again, O is the prediction, Y is the target, and we've observed Y in our training data set. Okay, so now the fun, if you can call it fun, starts. As an aside, when I was doing my PhD, we didn't have all these fancy libraries that automatically compute gradients, so most of my research time was spent implementing partial derivatives of various complicated neural networks. But nowadays, you don't have to do all of that because there's tools that do it automatically, which is really awesome and has contributed a lot to advancing research in NLP over the last couple of years. So we'll get to that a little bit more in another video where I go through how you actually code up these things in PyTorch. Okay, but not to get too off track here. In our example, we have just two parameters, w sub 1 and w sub 2. So all we want to do is compute, what just happened? Okay, dl dw sub 1 and dl dw sub 2, right? I want to compute these two partial derivatives. Okay, so let's start with the actual math portion here. How do I compute these two things? Let's work our way backwards. This is generally what we do. So going from the output, we'll go back like this, in that direction. And so the first parameter we encounter here is w sub 2. So let's start computing that derivative first, and then we'll get to w sub 1. All right. Okay, just this to be consistent. Okay, so start with this one. And an important concept to note here, we've already gone over the chain rule of probability, but important in these kinds of computations is the chain rule of calculus. So for those of you who have forgotten what this is, it basically says if I want to differentiate some function that itself is this kind of composed function, two functions composed together. So here, if I want to differentiate g of f of x with respect to x, this is equivalent to the derivative of g of x with respect to x, with respect to f. I can just undo f times the derivative of f with respect to x. Okay, so this is a basic thing that you likely learned in calculus, but it's going to be incredibly useful for everything we do after this point in the lecture. Okay, and again, this means this notation means partial derivative with respect to x. Okay, so we know our loss function is this. And we also know that O here is a function of w sub 2. Okay, so we kind of work our way back. We have this loss function, we go over here, and then we see that w2 occurs here. So the first thing we're going to do, let me make this easier to read, is define an intermediate variable which will make applying the chain rule a little more intuitive. Oh, let me use the same color. Wow. Redo. Okay, as you can see, I'm still not super confident with this interface. Let's say A equals W2H, where A is an intermediate variable. Now we can rewrite this equation as O equals tan H of A. All right, so now let's go through all of this and work our way back and apply the chain rule to actually compute this partial derivative. dl dw2 equals, the first thing we encounter is this O, right? We know O is a function of w sub 2, so we're going to do dO, but remember that O is actually two functions, right? It's this w sub 2 times h, and then the tan h applied on top of that. So we introduce this intermediate variable A. We're going to take the derivative with respect to A, and then finally take the derivative with respect to w sub 2. This whole process, we use the chain rule to get these equations. If you didn't follow that, you should go over this to completely understand what is happening here. All right, so let's start with this derivative here. dl do, if you look at L, this is pretty straightforward, right? We're gonna take this exponent, multiply it with the 1/2. The 1/2 is essentially there to just get rid of this constant term. We see that the O is also negated here. So the derivative total is just this. And now dO dA, right? So this we're not going to actually derive. This is just a little thing that you should know, is that derivative of x, the derivative tan h of x with respect to x is 1 minus tan h squared x. Like this. So a nice property of this function tan h is that it's its derivative it includes the computation of the original function. So there's no need for me to compute tan h of x again to compute the derivative, because all I have to do is just square it, square the original computation. So based on this equation, all I have to do is 1 minus O squared. So you can see how I didn't need to do anything fancy here. I already computed O in the forward pass, and now I just do 1 minus O squared in the backward pass to compute this derivative. And finally, dA dW2, we know that A is just W2 times H, so the partial derivative of A with respect to W sub 2 is H. So there you go. This is the full derivative of the loss function with respect to W sub 2. All right, so we also have another function, right? We have dL dW sub 1. And if we look back at our diagram here, we know that W sub 1 is used in the computation of H, right? This initial computation of H. So we need to work our way back one more step from where we were previously. And this is where the intuition of backprop comes into play. So if we work our way back, also note that this H again is a kind of composed function of tan H and the product of W1 and X. So before we start, let's just, when did we do this before? Yes. We'll introduce another intermediate variable. Intermediate variable B equals W1X. Right? So whatever is inside of this tan H term for computing H. Okay, so now that we have intermediate variable A and intermediate variable B, we can just write this out. It's dL dO, dO dA. So we're at this point, and now we see that A is W2H, but this time we don't want to differentiate with respect to W sub 2, right? Because we know that H is itself a function of W sub 1. So here we depart from what we did previously, and we do this. And now we know that H is made up of this intermediate variable, which itself includes this computation of dW sub 1. So if I were to compute all of these individual derivatives and multiply them together, I would get the partial derivative of L with respect to W sub 1. Okay, so the key point in backprop, one of the key points, is that if you look at these two equations here, there are some common terms, right? So specifically, these two terms are shared for both computations. Therefore, I can cache this from the computation of dL dW sub 2, and all I have to do is compute these terms. So you can probably see how if I have a very, very long network with many different functions and layers and so on, how this intuition helps, right? Because if I can cache a large percentage of the terms in this product, then I don't have to do those computations from scratch anymore. I save a lot of time. And so this is one of the intuitions behind backpropagation, right? We start from the very top of the network, the output layer, and work our way backwards so that we are able to use the cache derivatives of what I just computed to speedily compute a derivative further of a parameter that's used further down in the network. So I'll write that again. Oh, what is happening? Oh no, my pen has failed to write. Oh, okay. Okay, so intuition for backprop. Cache derivatives that appear higher up in the network and use them to compute lower level groups. When I say things like high level and low level, I'm referring specifically to essentially the distance from the output layer. So things that are close to the output layer are up high, and things that are farther down are low level. So in our neural language model, the most low level parameters are the word embeddings themselves, right? They're the furthest away from the end word prediction. Okay, so then just as an example of the parameter update step, remember from before in my gradient descent thing, where is that? Oops. Here, I have this update equation, right? So how do I apply this update equation down here? Well, it's pretty straightforward, right? Now that I've computed these partial derivatives, I can make a new w sub 1 by taking the old value of it, subtracting, oh, whoops, that's not the right way to write an eta. Learning rate times this partial derivative. Similarly, word 2 new is word 2 old minus dl dw sub 2. So this is the parameter update stage. Okay, so at least this part of, just want to make sure I didn't incorrectly, okay. So at least to this point, things should be fairly clear. We've dealt with a very simple example, and the derivatives were also fairly straightforward. If you're having some issues with this part, you should almost certainly spend the time to understand it, because this is essentially the core algorithm that all of the models we'll be discussing for the rest of the semester use for training. Okay, so for the last part of this lecture video, I know it's already kind of long, hopefully I can get through this in not too much time. I wanted to give some intuition on how this works when we're not talking about single neurons anymore, but we're talking about multiple neurons. So this is much closer to the setting of our neural language model. So specifically here, we're going to move away from these scalars to the matrix vector notation that we saw in the slides from last time. So for this part, I'm not going to derive the gradient for like the fixed window neural language model. I wanted to go over just how do we derive the partial derivative for a very commonly used component in these models, the linear layer, which we already saw in that model. So linear layer, simple component of NNs, is used in the neural language model to project that concatenated representation to the hidden space. And we're going to look at the definition as follows. Here, W is our weight matrix, and X is a matrix of a training example. So this also will serve to introduce the concept of batched training. So here we'll call this the input matrix, I guess. Okay, so now we no longer have scalars. Both of these X and W things here are matrices, but W is the parameter that we're interested in. Okay, so I guess I'll just highlight that linear layer. I'm talking about this. This is also called feed-forward layer or fully connected layer, so on. Okay. You also might see this with the order of the product switched around. So W of WX. Sorry, Y equals F of WX. But we're going to go with this because it makes the derivation a little more straightforward. But yeah, in practice, this general concept applies in general. So what do I mean by input matrix? This is a concept that we haven't talked about to this point. Ugh, why does my pen keep breaking? Start working again. Okay, so what do I mean by input matrix, right? What does this contain? So I mean that each row of X contains a vector that corresponds to a single training example. And this whole collection of examples that occurs in X is called a batch. So that is some terminology that we'll see over and over again. So in modern neural networks, we don't, like we did up here, put single inputs through a model at a time. So instead, we feed a batch of examples through the model, estimate the gradient on that entire batch of inputs, and then do the update. So this is often referred to as mini batch gradient descent or batch gradient descent. And another important hyperparameter here is the batch size of the model, which means how many examples are you going to have per batch. This is going to determine the number of rows in your X matrix. So what are these vectors? It kind of depends on where in the model you are, where this linear layer is. In our neural language model example, we use a linear layer to project the concatenated representation of the embeddings into some hidden space. So in this case, the X matrix could contain concatenated representations for a bunch of different prefixes, right? So each row contains a concatenated representation of a different training prefix. Okay, so let's introduce some variables here. N is a number of examples, or the batch size. Let's say D is the dimensionality of the whatever is in the X, the dimensionality of the vectors. We'll just say dimensionality of hidden space. And okay, let's say all right, maybe we'll make this more similar to the example and say D is a dimensionality of embeddings and M is dimensionality of hidden. The actual for this example, these two don't matter. This is a more general example. So let's say we have a toy example where N is 2, D is also 2, and M is 3. So this example is inspired by one of Justin Johnson's notes. He's a professor in computer vision at Michigan. But I think this is a great example to demonstrate some of the tricks that are incorporated into backpropagation when you go from scalars to matrices. Okay, so let's say we have a matrix X. In our case, X, the input matrix is a number of examples in the batch, which is N by the dimensionality of, say, the embeddings. This could just be the input, so it's a 2 by 2 matrix. And if we write out each element of the matrix, we get something like this. I think that's a 2. Let's also say we have a W matrix. So this W is trying to project these X vectors into this hidden space of M dimensions. Therefore, W is a 2 by 3 matrix. So it looks like 1, 1, W1, 2, W1, 3, W2, 1, W2, 2, W2, 3. This is a 2. Okay. And let's say, just to make things easy, that this f is going to be an identity function. F of x equals x. So we're not going to have to deal with chain ruling another nonlinear function. Okay, so we're interested in this y, right? Y is the output. And what does y look like, since it's the product of x and w? If we write out the terms in y, first of all, what is its dimensionality? You've now seen this in homework 0, right? We're taking this 2 by 2 matrix, multiplying it by a 2 by 3 matrix. Therefore, the resulting matrix is also a 2 by 3 matrix. So when we compute this product, we get x11 times w11, right? These two plus x12, w21. And this is the first element of our matrix here. So let's look at the second. So here we are multiplying this row by this column. Sorry, this first row by this column. So it's x11, w12 plus x12, w22, and so on. And at the bottom, let's just fill in the last cell. Here it's x21, w13 plus x22, w23. Okay. So this is what y actually looks like, right? And let's assume we're given dl dy. So this is the partial derivative of some loss function with respect to y. So we're ignoring all of the rest of the computations in this network. Let's just assume we've already computed this through backprop, and now we're at the point. And let's say we want to compute. I mean, there are two things of interest here: dl dx and dl dw. Right? How do we do this? Let's look at this one first. We know through the chain rule that dl dx simply is dl dy, which we said we already had, and we multiply that by dy dx, right? So this follows from the chain rule, and this term here is called the Jacobian. So the Jacobian matrix is essentially every element of y differentiated with respect to every element of x. And so in practice, actually forming the Jacobian matrix can be impractical, right? Let's think about the size of this matrix, since it's every element of y, right? How many things are in y? Y is an n by m matrix. And then every element of x, which is an n by d matrix. Right? So you can imagine on the scale at which modern neural networks, neural language models are trained at, we don't want to be forming this kind of matrix. We're going to run out of memory pretty fast with deeper models. And so the whole point of this current exercise is to show you how you can compute dl dx without explicitly forming dy dx. So oops. Sorry, the pen is acting up. Okay, there it is. I guess I will edit that out. But the point is we can compute dl dx without forming dy dx. Of course, to demonstrate this, because in this toy example it is feasible to look at this Jacobian matrix, let's just proceed by forming dy dx, and then this will give you some intuition on why we don't have to form it in the future. So dl dx equals, so remember this is what we want to compute, this is our goal. First of all, the partial derivative of the loss with respect to some perimeter is going to be the same dimensionality as that perimeter. So since x here is a 2 by 2 matrix, dl dx is also going to be a 2 by 2 matrix, and we can explicitly represent each element of this matrix with these scalars dl dx11, dl dx12, and so on. So we're interested in computing these four elements, and let's look at what actually happens if you want to individually compute each of these four numbers. So we can start with this one, dl dx11. And so we know from our equation up here that this is the same as a multiplication of dl dy times dy dx11. So note that L is a scalar here and X is a scalar. So this whole thing is also a scalar. And we want a way to get a scalar out of this. And we know that dl dy is going to be a 2 by 3 matrix because it's the same shape as y. And we can also write this term here as a 2 by 3 matrix and compute this scalar with a element-wise product of these two. I'm sorry, the dot product. So if we go over here, let's expand out what this term looks like. I said we can represent it as a 2 by 3 matrix. So if you look at the elements of y, which we wrote up here, you'll see that we have, if we're differentiating with respect to x11, this is an x11, and this is an x11, and it also occurs here. So the occurrences of x sub 11 are all in the top row of this y matrix. And you can look at what is being multiplied with x11 to get an idea of what the derivative is. So here it's w11, here w12, and in this case w13. So we get w11, w12, and w13. And in the second row, note that there are no occurrences of x11, right? Now we're in the second row, so we're looking at x21 instead, or x22, x23. So all of these terms are 0. Okay, so if we do the same exercise for x, say 1, 2, we can expand out this x12 term here, and it looks like this. Oops, that is a 2, 1, 2. These are all zeros. Similarly, if we do, let's look at one of them on the bottom row, so x21. And this term looks like this. So here the top elements are 0. The bottom elements are this. And finally, let's just not even, I guess we can do the last one. And what is this thing? It's It's again zeros on the top, but we have this on the bottom. So we've computed these elements of the Jacobian. Okay, so we've looked at the second term of this product, right? Of these products, these elements of the Jacobian. Now let's look at what this is, this dl dy. So remember that we're given this, right? So we can also just break this down into a bunch of different elements. dl dy11. Remember, this is going to be a 2x3 matrix. Because y is a 2x3 matrix. This one is 2, 1. Oops. 2. All right. So now we're just going to take the dot product of these two things. So we have this up here. And if we do dl dy times dy dx11, we get dl dy11 times w11, right? This is the first element here. And then we're going to add that to dl dy12 times w12 plus dl dy13 w13. Okay, so at this point, we can substitute this into the first element of our dl dx matrix. So let's make that more clear with some highlighting. So this term here is now replaceable with this term here. So if we rewrite now this dl dx using what we've just computed, first we'll plug in this green part. And then the second element kind of just follows. We're now using this matrix for the dx sub 1, 2. So that one, maybe I can be more economical in how I write it, is dy11 w21 plus dl dy 1, 2 w22 plus, okay, looks like I can't, 3. Okay, so similarly, let's just write the, okay, so this is supposed to be one cell here. Let me just divide these to make it more clear. And we can also just write out this one in case you want to go back and make sense of this. dy22 w22 plus dl dy23 w23. All right, that's a little messy. Okay, so we get this derivation of dl dx, and we did this by forming these intermediate matrices here. But the key intuition here, the takeaway, is that this can just be rewritten as matrix, as the matrix product of dl dy, which we're given again, dl dy21, dl dy22, and the transpose of the weight matrix, so w11, w21, w12, w22, w22, sorry, this is w13, w23. So if you go back and look at our original weight matrix here, this matrix is just the transpose over here. And so just to be clear, if you look at the first term in this product, right, this is a 2 by 3 matrix multiplied by a 3 by 2 matrix. So the end result is a 2 by 2 matrix, which again is what we want for dl dx. And let's look at the first element, this thing here. This is just the dot product between this row vector and this column vector, right? And the same is true for all of the other values in dl dx. So the important thing here is that we can just simply rewrite dl dx as dl dy times the transpose of the weight matrix. So in practice, we do this instead of computing the Jacobian, because this is far more efficient. If you want an exercise, you can compute dl dw. The solution is kind of follows from this. It's the transpose of the X matrix times dl dy. Okay, so what have we covered today? We've covered gradient descent, right? This is important. You should definitely know how this works. You should be able to implement backprop for a single neuron network. So this is all scalars, and you should be able to understand generally what's going on in the matrix vector setting, especially this concept of batches. We're not going to actually test you on whether you can, derive these gradients in the matrix vector setting, but it's an important concept. This is what's happening in the background, right? So we also covered backprop, and the key takeaways of backprop are chain rule, that's major component, and also caching these intermediate derivatives. And finally, using efficient computations to avoid, when you can, forming Jacobian. So this latter part, where we derived these updates for the linear layer, these are kind of the things that are happening in the background when you use something like PyTorch to compute derivatives. So it's important to know what's going on. Okay, so for next time, next week, we'll be looking at first an implementation of the single neuron case using PyTorch, and we'll also go over the loss function training objective that's used for language modeling. And we will start our introduction to the transformer model, which is the final model that we'll be covering in this semester.